Okay, so the last couple of classes we've talked about central tendency and power. So today we're going to show you how to do some measures of central tendency and also how to calculate power using R. Let's start with a quick review. So the last time we had the stats lab, we learned about the probability mass function, right, for the binomial. So does anyone remember the name of the function that we used? It wasn't pbinom. dbinom, that's exactly right. So to get the probability masses, we used dbinom. And we told it how many successes that we had observed, that would be a sample statistic. We told it the number of observations. This is a parameter that we set when we determined how many flips we were going to do or how many statistical experiments we were going to do. And finally we told it the probability of success. This is given by the null hypothesis, right? Okay. So, the probability mass function, for 10 flips of a fair coin, we can generate this really easily. So, go ahead and do this. So, probs equals pbinom, 0 to 10, comma 10, comma 0.5. Yeah. Did you guys get anything? What does it look like? 9.5. Oh, are these the values? Did you do the plot? Ah, okay. So you got 10 values, or actually 11 values, right? So you get the probability mass for 0 successes, the probability mass for 1 success, the probability mass for 2, 3, 4, all the way up to 10 successes. Then if you type in this plot, 0 to 10, probs, it's not a histogram because we don't have bars that are touching one another, right? We've got these points, right? And it looks kind of like a bell-shaped curve. It looks fairly similar to that. So you should have something that looks like this. Now, last class, what we were doing is we were asking what's the p-value for some observation. So we said, okay, imagine that we have this observation and we want to know the p-value for that, right? We said, well, if it's a two-tailed hypothesis, what we're going to do is we're going to sum up all of the probabilities that are at this level or below, right? So we would add those and add those. Now we're going to ask something different. Instead of asking what the p-value for some observation is, we're going to ask what observations will result in a p-value that's less than or equal to alpha, or alpha divided by 2 if we're talking about a two-tailed hypothesis. So we're looking at things a little bit differently today. So how could we do this if alpha equaled 0.05? Does anyone have an idea? How can you figure out, by looking at this, what observations should have p-values that are less than or equal to 0.05?
So we can draw a line.
Okay, we can draw a line. Where? At like 0.05? Okay, so if we drew a line for 0.05, right? Now, we would want to add up everything underneath that. Now let's do that. Let's take these first. So what's the probability for this?
0.05.
It's close to 0.05. So we want to add up everything that or more extreme. So this is also that or more extreme, right? So if you added up something that's close to 0.05 and something else that's close to 0.05, what's the resulting probability going to be? Something that's close to 0.1, right? Now is 0.1 greater than alpha? Yeah, so we probably don't want to draw our line through at alpha, right? Because if we drew it through at alpha, we would add these two in, which would already push the p-value up over 5, not to mention these. We have the right sort of idea. You know, maybe there's some line that we could put in. Are there any values that are really small? So these are both really small. If you added both of those up, imagine stacking 2 of those on top of one another, right? That would probably, well, if we stack those 2 on top of one another, the p-value would be less than 0.05. So maybe we could stack those on top of one another, and then those two on as well, maybe that would give us also something that's beneath 0.05. So that's sort of what we're going to be doing. Now, for a two-tailed alpha of 0.05, in the lower tail, right, we have 0.05 alpha total. Since we have two tails, we want to put half of the alpha in our lower tail and half of the alpha in the bigger tail, right? So if we just look at one tail at a time, we can just sum up one part of the tail at a time, right? Looking for p-values instead of being less than or equal to 0.05, looking for p-values that are less than or equal to alpha divided by 2, so 0.025, right, instead of 0.05. So we're going to reject the null hypothesis if the probability of observing that many or fewer successes in the lower tail is less than or equal to 0.025. Now to get these probabilities, all that we have to do is add up the probabilities for some number of successes and all of the probabilities for fewer than that number of successes, right? So if we have 0 successes, we add up 0. Well, there's nothing lower than 0, so that is what it is. If we had 1 success, we would add up the probability of 0 successes to the probability of 1 success, and there we have it. If we had 2 successes, we would add up the probabilities for 0, 1, and 2 successes. Does that make sense? So this is what we're going to do to figure out the p-values for just one side. Okay, so I don't want you guys to type all this in right now. You can do this later. But let me grab some of this. I'm just going to copy and paste this into R. Okay, so I'm creating a variable sprops for like some probabilities, right? Because all we're doing is adding up probabilities, so we're creating some. So sprops. Now the probability for the first sprop, that is the probability of all 0 successes and fewer, well that's just dbinom 0, 10, 0.5, right? The probability mass for 0 successes. So if we look at sprops right now, we have one value, right? Now, what we can do now is do this funky little thing. And what I'm doing here is I'm saying, okay, the sprops is going to equal, now I'm concatenating things, so it's equal to the sprops what it was before, so it's equal to this, and now I'm also including the sum of the dbinom, so the sum of the probabilities for the 0 and first successes, right? So I'm adding this success to one success to get the second value. So if I look at sprops after this, I should have 2 values. Uh-oh, misspelled. sprops. There we go. There's the 2 values. So if I do this a third time, I'm saying sprops now is going to be this, with the next term is going to be the sum of the probability of 0 successes, plus the probability of 1 success, plus the probability of 2 successes. So if I look at sprops, now I have 3. Now I don't need to keep saying this, I hope. So let's just grab the rest of them. So I did 0, 1, and 2, right? Now let's take a look at sprops. Well, they start down very close to 0. 0.00097, and they go all the way up to 1. Which they should. Right? The last thing I'm adding up is the sum of the probabilities for 0 successes, 1 success, 2 success, all the way up to 10. Well, those things are complementary together, right? They fill up, they entirely exhaust the space, so they should add up to 1. Now that we have this information, we can see what S-probs looks like. So before we had this nice sort of like bell-shaped curve, and now if we plot S-probs, instead we have something that looks like this. It looks like an S sort of tilted on its side. So what's happening? Okay, so we have the probability for the first. Now we have the probability for the first and the second. The probability for the first, second, and the third, right? And we keep adding them. Now, this keeps going up because we keep adding more and more, right? Now the probabilities, when we had this function like this, at both ends they were very tiny. So at both ends, we're just increasing a little bit. But in the middle, we're going up pretty fast, right? So now we've got a graph of S-probs. So what we can do is draw a line through at alpha divided by 2. We said our alpha was 0.05. So our alpha divided by 2 is 0.025. So if we do that, 0.025 should be down here somewhere. And then we should be able to reject the null hypothesis whenever we observe successes that fall beneath that line. Right? Because any success that falls beneath that line has a cumulative probability that's less than the alpha that we're putting in that tail, which is exactly what we're looking for. So if we draw this line in, which 2 points do we see beneath it? We see the first 2. So we would reject the null hypothesis for a two-tailed test with an alpha 0.05 if we observe 0 successes or if we observe 1 success. So the cutoff for the lower limit is 1. If it falls on or below 1, we are rejecting the null hypothesis. Okay? So this cutoff, we're going to call this a critical value. This is a critical value for the lower tail. And here the critical value is 1 success. Now, the upper tail, we also want to get the top 2.5% of the mass, right? So how could we figure that out? So maybe we could draw a line through 1 minus 0.025, right? Because this is 1, and we want 0.025 beneath that, right? To capture the top 0.025. So maybe we could draw a line 0.025 beneath that, and just like for this, we said we're going to reject if it's below the line, maybe we could say that we're going to reject if it's on or above the line. Does that make sense? So if that's the case, what would our cutoffs be? Or what would our critical value for the upper end be? If we're going to reject when the dot falls on or above the line, when are we going to reject? For the last 2.
3.
Not the last 3 or last 2?
3.
Let's have a vote. 3 or 2? Okay, how many people say 3? How many people say 2? It's like one sort of strong 2 and a couple weak 2s. Actually, the 2s are right. The 2s are right. Those of you who said 3 are wrong. This is the wrong way to do it. The idea of plotting this line is right on, but just saying that anything that's on or above this line will qualify won't work. That's not going to work. That's going to be wrong. So this is 10, 9, 8. 8 is not the upper critical value. So you said 2. What do you think the upper critical value is? 8 point something? But we don't have any 8 point something. 9. She's right. The upper critical value is 9. Now the big question is, why? So for the lower one, we said, okay, we're going to take anything that's on or below that line. So why isn't it just anything that's on or above that line?
So we want to take them as equal.
Mm-hmm.
If we take under the line from 2 and above the line, we take 2.
Yeah. So this isn't always the case. So she said we're going to take 2 under the line, so we should be taking 2 above the line too. Right? Now, this distribution that I plotted, the probability of success was what? P success. This was determined by the null hypothesis. That's the only way I was able to come up with these graphs, is because I knew what the null hypothesis said it was. So what did the null hypothesis? Not 2 outcomes. The null hypothesis said something about the probability of the outcomes. Probability of success was?
Minus 0.1 alpha.
No.
Not minus.
Yes, the probability of success was 0.5. So we had a really nice symmetric distribution. When we have a symmetric distribution, the cutoffs should cut off the same amount on both ends, right? But up here it looks like it's actually cutting off more. And I really did draw the line through here. You can look at the code, I posted it online, you can draw it yourself, and you'll see that it cuts off 3. So why is this? Well, this point shows the sum of all masses up to and including that number. So this shows all the mass up to and including that. This shows all the mass up to and including that. All the mass up to and including that. So this one actually includes mass from this point all the way up to here. So really it's containing, it's sort of like crossing the border. It's just pointed as one thing, but it has mass to push it up over, right? So let me read it. It took me a while to write this, so it will be better if I read it. So this point shows the sum of all the mass up to this number of successes. Subtracting this sum from 1 shows us how much the sums of the other 2 will be. Okay, so if we subtract this from 1, this should leave us with the remaining mass, right? So this shows us that the sum of the points beyond this will be less than alpha is alpha divided by 2. So therefore, this point, the next point, will be our upper critical value. And we can prove to this by calculating things in a backwards sort of way. So, notice that this first term, before I just said S probs is equal to dbinom 0, 10.5, right? Now here I'm going backwards. I'm starting with the 10. But notice I'm not starting from 0 and adding, I'm starting from 1 and subtracting. Okay? So, boom. Let's see what S probs is. S probs, so that's 0.99. Let's subtract that from 1 for just a second. 1 minus S probs. What does that give us? 0.9765625. Oh my goodness. This is exactly the same probability as that was. So subtracting, starting from 1 and subtracting, is giving us the same probability as starting from 0 and adding. It's working this way because we have this symmetric distribution. Okay, so now I'm going to put on the next one. But I want to keep the ordering of things. So before, when I did this concatenation, I said S probs equals S probs and then the other thing. Now I want to put S probs on the end because this is the 10th, right? So I want to have this last. So I'm going to put that here, and here what I'm going to do is I'm going to add up the probabilities for 10 successes and 9 successes and then subtract that from 1. Okay? So if we look at S probs, actually let me do 1 minus S probs. 0.01074. Oh my goodness, oh my goodness. That's the same thing that we had before when we were going from 0 and up. Alright, so let's quit the tomfoolery and do all of the rest of them in one fell swoop. Wow! That's probably bottom. A lot. 0, 10, S probs. looks very similar to what we had before, right? So here I've got it on the PowerPoint. And now this looks about the same, right? About the same. Now let's see if it actually is. Let's plot our lines through this thing. So if we put our lines through it, what do we have now? Well, look, we've got 2 up at the top and 3 down here. Right? So when we were summing up these things, when we had this value here, right? This contains all of this mass plus this. And by having this much more mass, when we go the other way, we see that this really contains more than our 0.025% that we were looking to have. So, you know, it's too bad, it's such a pain in the butt to do this. That was a whole hassle, right? Wish R had a better way. What if there are any other functions? You said some other function earlier today, didn't you? Pbinom. Pbinom. What is pbinom? Pbinom was calculating cumulative probabilities. So, wow. Pbinom is the cumulative probability mass function. So if we do this, plot, go ahead and do this. It's the same thing that I had. That's exactly right. So boom, that's it. Pbinom does this for us. This is nice because this means that we don't have to go and add up all these probabilities by ourselves. Pbinom will handle it. Pardon? Huh, you don't have the lines because you haven't told it to. To draw in the lines, do this. So if you want to put a line in at 0.025, type this, AB line, H means horizontal, V means vertical, H equals 0.025. So that will make a horizontal line at 0.025. You should get that. If you want the top one, it would be H equals 0.975. Right? 1 minus 0.025 is 0.975. Then you can type, if you want to change the color, comma, col for color equals purple, or green, or whatever. And I'd like to make it thick. LWD, line width, equals 2. If you want to know how to change the color and change the thickness, and maybe you want to make it dashed because you're a spunky kind of person, all you have to do is type in question mark AB line, and that will give you R's help, and it will tell you what some of the different parameters are so you can change them. Okay. So this was back exactly where we started, and that really wasn't hard after all. So to get the critical values with cumulative probabilities, for the lower critical values, we're just going to look for the largest number of successes with the cumulative probability equal to or less than alpha if it's one-tailed and alpha divided by 2 if it's two-tailed. Right? That's what we did when we said, okay, which fell beneath when we had the ogive. I'm sorry, that S-shaped thing that's called the ogive. You don't need to know it. That's what it is. Anyway, so when we had that cumulative probability distribution and we plotted that line, things underneath there, the largest one was 1. So we said our critical value for our lower tail was 1. Now for the upper critical value, it's 1 more than the smallest number of successes with the cumulative probability equal to or greater than 1 minus A if it's one-tailed, or 1 minus A over 2 if it's two-tailed. Right? We had this thing, and we had something like this. And we said it wasn't this one, right? It was not that one. This was the smallest number of successes that had the cumulative probability, but that wasn't it. We wanted one more. So, with that, now I can tell you, okay, here's the hypothesis. Here is alpha. Here is our sample size. What are the cutoffs? And you can calculate them. If you want to see an R implementation of this, you can jump online and download the R code for today. But there's a better way. R. It has a better way. There's a problem with pbinom. If you're trying to do it like by eyeballing it without using my fancy code. So if you have large sample sizes, so here we have 0 to 100, right? So we could potentially observe 100 successes or 0 successes. The probabilities are low, but we could. And the cumulative probability, the mass function looks like this. So which of those falls on the line? And which is the first one to fall on the line? It's hard to tell. They're circles, they're not points even. So we're trying to figure out which one has the middle that's on the line or just above it. So trying to eyeball something like this can be really, really hard, right? Be a pain in the butt. So let's see if we can do something different. We can use qbinom. Qbinom is going to tell you the number of successes that's associated with the cumulative probability of at least the quantile you provide. Okay, so quantile. Hold off on defining that for a moment. Let's take a look at what Wikipedia says about quantiles. There are several methods for estimating the quantiles. The most comprehensive breadth of methods is available in the R programming language. Not in SPSS, not in SAS, R. All right, so, that's great, but what's a quantile? So, a quantile is just a value that divides the distribution into chunks. We say 0.025, right? That divides the distribution into 2.5% and 97.5%, right? If you have ever received a percentile score for your performance on a test, a percentile is actually a quantile. It's a special type of quantile. It's funny, I used to never understand what the percent meant until I came to Turkey. And then you'd say like, yüzden yirmi, and it's like from 120. It's like, it's brilliant. It's part of the 100. It's the part of the 100. And then it's like, oh yeah, that's what a percent is. So when you guys took the test to get into college, you got your scores, right? Oh, I got a 438,222. Whatever. Do they give you a score like you're in the 99% or you're in the 50% or in the 70%? Do they do that?
Yes.
They do?
Yeah.
Okay, those are percentile scores. The percentile scores, those are based on 100 quantiles. So if you scored in the 95th percentile, what that means is that 95% of the people did as good or worse than you did. Right? Pardon? Or worse.
How does it work?
How does it work?
Yeah.
How does it work? Anyone want to take a guess? Not with R, not with R. We need to think about what it is before we do it in R, so we can understand what it is we're doing in R. Because otherwise we're just a bunch of monkeys pressing buttons.
I thought it's like you did better than 95% of the people. Not like there are like 95% people who did as good as you or worse.
Yeah, it's interesting. If you look on the internet, you see two types of definitions. You have some definitions that say it like this. And you have the other ones that just say you're better than 95% of the people. But if you're in the 95th percentile, and there are lots and lots and lots of other people who took the test, there are lots of other people who are in that percentile too, right? So like, it might not be right at, it could be that exactly 95% are below you. But it could also be that some of them are in that group too. Because this is a cumulative probability function. The quantile is a cumulative probability function. So just like here, when we had this, we had 1, 2, 3, and we had our cutoff. This was 0.975, right? This value, we can say that that's the 0.975 quantile. It contains 97.5% of the people, right? Actually contains more than 97.5, because there's the 97.5 here, but then there's this little bit here too. So it's actually like 97.58. Does that make sense? Kind of. No. All right. Let's see if I can come up with that. Yes?
What if it's not a regular distribution? But if 95% of people, all of them get 9 or 90%?
If 95% of the people get 90, I'm not sure I follow your question.
If you take 95 and you think I'm very up, but what if no one gets under the 60, 70?
Okay. I'm not sure if this is what you're saying, but it has inspired me, so thank you. If this is what you're saying, then you're right on. So imagine we have some distribution like this. I'm making a big wide bar. I should make them equal width. I'll make them equal width. I'll try to make them equal width. So, there are lots and lots and lots and lots and lots and lots of people here.
Yeah.
If we want the 50th, if we want the median of this distribution, the median, it's in here, right? So 50% of the people fall in or below there. Also, 60% of the people fall in or below there. Also, I have to figure out exactly the heights and everything. By trying to draw it in such a way that it's possible that 90% of the people, actually, yeah, this is one of the things that height. Right? So this contains more than 90% of the observations. So, if everyone got the lower score, except for like one person, then this could contain the 95th percentile. Right? Because the 95th percentile fits in or beneath that. Does that make sense? Yeah? Is anyone else still doubting? Let's do an easy 2-coin flip. Fair coin. What are our possible events? We have heads and tails. Tails, tails. Heads, heads. Tails, heads, right? So if we want to draw the probability density function, let's see, 0.5, 0.25, for 0 successes, let's say tails is a success. So this would be a heads, heads. What's the probability? 0.25, right? Now, for 1 success, this would be heads, tails, tails, heads. What's the probability? 0.5. And for 2 successes, so this is tails, tails. What's the probability? 0.2. Yes, that's right. Okay, so where's the median? The median is actually a quantile. There is no value that, like, you say, like, oh, well, 1 cuts off half, you know, and half is exactly beneath 1 and half is exactly above 1. No, half is beneath and included in 1. Half is above and included in 1. Right? Does that help? Okay. So, if we want to rephrase this, it tells you that the cumulative probability, mass, or density, depending on what type of score you're talking about, was at least 95%. So if 95% of the people did as well or worse, then your score was at least 0.95. So at least. Imagine we do 30 flips of a fair coin. This is in question. This gives us our hypothesis. P success equals 0.5. It's going to be 2-tailed. Alpha equals 0.05. Now what we want is at most 2.5% of the mass for the lower critical value. And also at most 2.5% of the mass for the upper critical value. Right? But if we do this qbinom, so this is the quantile we're providing it, 0.025 for 30 observations with a 0.5 probability of success. It says that the probability of observing 10 or fewer successes is at least 0.025. So why don't you type this in? qbinom 0.025 10. That's where I got this. It says that this quantile is at or under 10. How about this? qbinom 0.975, 30.5. 20, right? So the probability of observing 20 or fewer successes is at least 0.975. That's what this qbinom is telling us. It's saying, okay, this is the quantile we're interested in. What's the number of successes that's associated with at least that many? Right? At least that much mass. Okay, so if we just go back and look at the upper critical values, this is what you just did, right? 20 was the answer. So let's look at this very closely. The probability of observing 20 or fewer successes is at least 0.975. We're interested in the upper tail. Is there anything that we know about the upper tail given this statement? If 20 contains at least 0.975, what does 21 contain? Do we know anything about 21? We do know something about 21.
0.025 or 1.
So if we know that the probability of observing 20 or fewer successes is at least 0.975, then the probability of observing 21 or more is at most 0.025. Does that make sense?
Yep.
So we're saying at 20, so here we go, 20, 21, and we say, okay, at 20, we have, at least, right? So at least 0.975, right? There could be more than that in 20. But there's at least that much, which means that 21, it can't have the 0.975, so it's got to be at most that, right? So if the 0.975 would fall on this end, the maximum value that 21 or more successes could have would be 1 minus this, which is 0.025, which is alpha divided by 2, which tells us What is this value? If that value has, at most, 0.025% of the mass, and our alpha for the upper part is 0.025, what do we know? What would we do if we observe that?
Reject.
We would reject the null. That's right. 21 or more, that's what we want. We want at most 0.025. So 21 is our critical value. If we're looking at the lower values. So the probability of observing 10 or fewer successes is at least 0.025. This is sort of the same thing I said earlier, except now the number's different because this is the quantile that I'm using, right? And this is the value that it gives us. So we're not interested in things that are above. I mean, based on this, we could say that the probability of observing 10 or more is at most 0.0975, but we're not interested in what's above for the lower tail. We're interested in what's below, right? So if it's at least 0.025, what do we know about 9 or fewer successes? Do we know anything? We're going to fail to reject with 9? No? She's right. You're going to fail to reject with 9. There's one other trick. So the probability of observing 9 or more successes is less than 0.025. Right? Now what we want to reject, we want to reject the null when the probability of observing something in this lower tail, the cumulative probability for that, is not just less, but less than or equal to. Right? So we know that 0.9 is less. So we know that we'll reject when we get when we get 9. We know we'll reject when we get 8, 7, 6, 5, 4, 3, 2, 1, 0. Right? So you're absolutely right. We will reject. Now the question is, might we reject for 10? We might. We could. We want at most 0.025. Now, we can tell if the probability of observing 10 or fewer successes is exactly 0.25. How can we do this? What argument would tell us what the probability of observing 10 or fewer successes is? To get the probability of 10 or fewer successes, what do we have to do? We get the probability for for 20 successes. We get the probability for 10 successes. Yes. And then what do we do? And we're going to add what are we going to add? Probability of 11 successes? What? What am I going to add then? I'm going to add up all the probabilities from 0 to 10. So probability of 0 successes, probability of 1 success, probability of 2 success, probability of 3, 4, 10. You're going to add up all those things. Do we have something that does it for us?
Yeah.
Yes, what is it? Pbinom. Pbinom. Yes. Pbinom is back to the rescue. So we do this. Okay, type it in. Pbinom 10, 30, 0.5. If pbinom of this is equal to 0.025, it's not equal to it. Is it less than?
Yes. Yes.
No, more.
It's less than?
More than.
I want to make sure that you did this right. The pbinom for this should not be less than. If it is, I'm teaching something wrong or R is doing something wrong. Because it should tell us that the probability is at least 0.025. So this should be 0.025 or maybe 0.026, 0.027, or 0.028, 39274, whatever. It's greater. It's about 0.049. Oh, it's a lot bigger. It tells us that the probabilities of observing 10 or fewer successes is almost 5% of the time. Right? The probability of observing 10 or fewer is 0.05. Well, our alpha is 0.05, but we're only looking at the lower tail now. So we're not comparing it to 0.05, we're comparing it to 0.0245. Yes. Is that bigger than 0.025? So we should fail to reject with 10, right? Now, Gosde already told us that of course we're going to reject when it's 9. She knew that. So 9 must be our critical value because we're not rejecting it here, but we are here. Thank you very much. Okay, so we put it all together. To find our upper critical value, we're just going to add 1 to qbinom. 1 minus the quantile. Remember I put in 0.975 to get that upper 2.5%. So qbinom 0.975 for the sample size, and the probability of success is given by our null hypothesis, and just add 1 to that, right? Yes? The file sizes of these things is like enormous. So for like Friday's or Wednesday's class, there's like 20 gigabytes. Oh, great, it's like Blu-ray. Alright, so thank you. Alright, so the upper critical value is the qbinom for 1 minus the quantile that we're interested in, and then we're going to add 1 to that. Right? So, to find our lower critical value, what do? We get qbinom for the quantile, not 1 minus, but just the quantile, 0.025. The sample size and probability of success. And then what we do is we put that in to pbinom to tell us whether this quantile cuts off more or exactly 0.025.
What will we add?
What will we add where? Here?
No.
What are we adding?
No, what will we add for qbinom? Will we add qbinom? What did you say?
Okay, so we do this, right? This gives us a number of successes. We take this number of successes and put that in here. Okay? And then we can see if that number of successes gives us exactly the quantile or something greater than the quantile. If it's something greater than the quantile, we're going to subtract 1. If it's exactly that quantile, you're done. You already know the number of successes. That's what qbinom gave you. Okay, so for a one-tailed test, the quantile is just alpha. For the two-tailed, the quantile is just alpha divided by 2. I'm not expecting you guys to like memorize, okay, quantile is equal to alpha for this. No, this is just a name for a variable that I'm putting into R. This, A and A divided by 2, this is the important stuff. You need to know that when you do a two-tailed test, you're using alpha divided by 2. When you're using a one-tailed test, use alpha. Okay? Now, doing all this can take some time. Okay, let's do the qbinom for this, and we're going to do the depth for this. Anyway, one of the great things about R is you can make your own functions. So I created my own function that you tell it what the probability of success is, you tell it what the sample size is, you tell it what the alpha is, and you tell it what tails you want, and it will automatically spit out the critical values, or it will even tell you, sorry, it will be impossible to ever reject the null hypothesis with the situation that you propose. So you can do something like that, and then when you're doing homework, if you have a whole bunch of critical values to compute, you just keep using the function. Anyway, the function is online. This is not required for this class that you learn how to use the functions, but it's important to know that the capability is there. If you're interested in checking it out, check it out, I'm more than willing to talk with you about how the details of this works. Okay, so why are we doing this? Well, we need the critical values to calculate something, and that something is power, right? And beta. Beta is just 1 minus power. Power is just 1 minus beta. Okay, so what is power? It's the probability that you would reject a null hypothesis for some specific alternative hypothesis, right? So all we need to do is add up the appropriate probabilities from the alternate probability mass function. Now, when we have the cutoffs, this is going to be ridiculously easy, at least compared to what we were doing earlier. So, which probabilities do we add up? Well, we're going to add up the probabilities that are at or beyond the critical values that we figured out in that last step. So, what do we need? Critical values. Do we have them? Yes. What were they? They were 9, 21. Great. We've got those. We need some specific alternative. Now, let's imagine that we observed... Okay. Let's say we observed 11 heads. Now, our best estimate for what the true probability of success is based on this would be 11 divided by 30, right? Based on the sample that we have, if we don't really know what the population is, our best estimate is the probability that we actually observe things, right? So with this, we actually have a specific alternative that we can use, right? How much power did we have to detect this, right? We're going to fail to reject the null hypothesis because we had 11 heads and 9 was our lower cutoff. All right, so how much power did we have? We can figure this out. So we can just plot the density function with our new values. So instead of 0.5, we use 11 divided by 30. Yeah?
So before this slide, you said 1, 6, 9, you fail to reject. But you know, you have to reject, or?
With 11, we should have failed to reject. We're only going to reject if we get 9 or fewer successes, or 21 or more successes. If it's 10 to 20, fail to reject. Not enough evidence.
Then we reject.
We're going to reject at or less than 9, at or above 21. Right? Those are our two tails. If I were to draw the previous distribution up here, it was something like that, right? We said, okay, so our cutoffs are at 9 and at 21, right? So if it's in this tail, reject. If it's in this tail, reject, right? All right, so let's plot the lines that cut off our critical regions. Boom, there they are. I guess I can have left that little thing up there. All right, so this means that we're going to reject the null hypothesis if we get a value out here. We're also going to reject the null hypothesis if we get a value here. Now, if the true probability really is 11 divided by 30, this is the distribution that we should see, and we can figure out the probability that we would correctly reject things. The probability that we would correctly reject things is just these probabilities summed up and these probabilities summed up. You don't add up the middle ones. You just add up the ones that are beyond, at or beyond the critical values. So, we can let R do this. We are running low on time, so I will just skip through. You guys can do the code after class to make sure it works for yourself. It's about 0.29, which means that 29% of the time that the probability of success really is 11 over 30, we would correctly reject the null hypothesis that the probability of success equals 0.5. It's not a whole lot of power. What's beta? 1 minus 0.29. So it's not 0.975. It's not the 1 minus alpha over 2. It's 1 minus this, 0.71. Yeah. Now what if the probability of success really was 0.2? What would the power be then? Well, then the power would be 0.94, and you can calculate this afterwards, which would mean, sorry, it should be 94% of the time the probability of success equals 0.2, we would correctly reject the null hypothesis that the probability was really 0.05. So beta here would be 0.06. Yeah. Okay. Ooh. The rest is actually really easy. I mean, the hard stuff is the stuff with the quantiles and the cumulative probabilities. The rest of this, I show you how to load some data into R. You download the data that's on my website. You put it in the directory. You set your working directory to that thing. Then you're going to use this data equals read.csv file, and then the name of the file, and it will load the data in for you. You can run through all this on your own. The whole point of getting these data out was to show you how easily it is to plot some histogram of data very quickly when you got it. And also how easy it is to calculate mean. So if you want to calculate the mean, there are a number of ways that you can do it. The easiest way is to do mean ages, if you want to get the mean of ages. There are some other variables, so you've got the mean of them as well. Same thing with medians. All you really need to do, so here's a really complicated way of doing it. The much easier way is just median, ages. Now median is a quantile. R has a function called quantile. And you can tell it, get the quantile of ages 0.5. That will give you the median. This should be the same thing. So you guys can check this out for yourself later. And you can take a look at that.